Welcome to this second lesson on errors in machine learning. All machine learning models come with a degree of uncertainty when predicting outcomes from new data. The difference between predicted and true values is what we aim to understand. Join me as we explore the types of errors and the notorious issue of overfitting. Take a look at the first two models in the figure. The simplest model assumes a constant value for all data points, while the second assumes a linear relationship. When these assumptions deviate from the true nature of the data, so-called bias creeps in. Bias represents the systematic errors introduced by these assumptions, creating a deviation from the correct values. It's crucial to note that bias isn't limited to mathematical assumptions alone. In AI models, bias can also arise from the training data itself. Take, for instance, a recruitment system trained on biased historical data. If that data favored male applicants, the model could inadvertently perpetuate gender bias, disadvantaging female candidates. Now shift your focus to the higher degree polynomial models on the bottom of the figure. The high degree polynomials perfectly fit to the training data. But the more complex the model, the more it tends to be influenced by the specific data it was trained on. Due to its sensitivity to variations, it fails to generalize well to new data. This phenomenon is known as variance. Now, the interesting part comes in balancing bias and variance. Simple models, while very robust, may not capture the complexity of underlying relationships, resulting in a high bias. We call this underfitting. Overly complex models, on the other hand, fit the trainer data perfectly, but may become too sensitive to variation, leading to poor generalization. We call this overfitting. Finding the right balance is what we call the bias-variance trade-off. In the world of machine learning, detecting overfitting is crucial. You've learned about splitting data, but let's take it up a notch with cross-validation. Imagine breaking down your labeled data into 10 subsets, for instance. Train the model with 9 subsets, test it with 1 and calculate the error. Repeat until each subset was used for testing once. This cross-validation method provides a reliable gauge of your model's quality, helping you identify overfitting more effectively. Beyond the traditional split between training and test data, cross-validation allows us to evaluate our models from various angles, ensuring they perform well on different subsets. The figure illustrates this method with 4 iterations, but typically 10 subsets are used. Here you have it. Bias and variance play a critical role in the success of machine learning models. It is important to find the delicate balance between bias and variance. Cross-validation can help build more robust models. Understanding these concepts is fundamental to building robust and effective AI systems. In our next lesson, we'll explore practical techniques for striking this delicate balance and improving model performance. Until then, happy exploring.